If you open a logistics app in any major city, you are looking at one of the hardest problems in software engineering. Coordinating millions of moving consumers, merchants, and couriers simultaneously across a grid requires pinpoint accuracy. But legacy web architecture was built to fetch and serve static documents, not to track constant physical motion. If millions of active devices are constantly sending traditional transactional queries to a relational database asking, "Where are you now?" the system will buckle. Database rows lock, latency spikes, and the map freezes. To handle this volume of continuous movement, engineers have to abandon standard database polling entirely and move toward an event-driven, streaming signal architecture. This requires synchronizing persistent network connections to bypass request overhead, rigorous spatial indexing to handle the math, and probabilistic map matching to correct real-world interference. We are going to architect this real-time stack from first principles. By tracing a single location ping from device ingestion to final client rendering, we can see exactly how this operates at scale. Scaling citywide logistics requires replacing how location state is communicated and processed across the entire network. The architecture begins at the edge of the network, isolating a single mobile device generating raw GPS coordinates. In a typical setup, the courier's application reads the hardware for a new latitude and longitude every 2 to 5 seconds. Maintaining this constant transmission rate creates an immediate constraint. It rapidly drains the mobile device's battery. To solve the battery drain problem, developers implement a mechanism called adaptive frequency. This graph plots transmission frequency on the Y against vehicle speed on the X. Adaptive frequency ties the ping rate to physical speed, polling frequently in motion. But when speed hits zero, like waiting at a traffic light, transmission frequency drops to a minimum baseline. This ingestion behavior defines event-driven architecture. Data is transmitted based on actual state changes in the physical world, rather than firing off pings on arbitrary fixed time intervals. Optimizing data ingestion directly at the source prevents the backend network from drowning in redundant static updates before the data even leaves the device. Moving up to the transport layer, the challenge is getting those ingested GPS pings to the backend server with absolute minimal latency. Standard HTTP polling requires a multi-step connection handshake for every single ping. Multiplied by millions of users, this creates an unacceptable amount of network overhead. To eliminate overhead, engineers rely on persistent connections. This diagram shows 3 primary network pipelines: server-sent events, WebSockets, and gRPC. Server-sent events, or SSE, operate as a unidirectional stream from server down to client. This is highly efficient for the consumer's app. The server pushes continuous location updates to the waiting customer without the customer sending heavy data back. WebSockets, by contrast, create a full duplexed, bidirectional open pipe. The courier app requires this setup, continuously sending raw GPS data up to the server while receiving live dispatch instructions back. Once the data hits the backend infrastructure, it travels via gRPC, a high-performance alternative designed specifically for internal microservice communication. The choice between a unidirectional or bidirectional persistent connection is dictated entirely by that node's function in the network. Selecting the precise transport protocol eliminates handshake latency, maintaining the high-speed persistence necessary for live logistics. Once the coordinate reaches the server via the WebSocket, it hits an in-memory data store, like Redis, allowing for microsecond access. Raw latitude and longitude coordinates are highly inefficient for routing. Continuous distance calculations on floating point numbers across millions of users requires massive computational power. To reduce this load, the system utilizes spatial indexing to mathematically normalize the geographic space. This diagram compares spatial indexing. Left is a traditional square grid, right is a hexagonal grid. In a square grid, the algorithm measures from one center point to its adjacent neighbors. This creates an inherent geometric flaw, a diagonal distortion. Diagonal neighbors are physically further away than horizontal or vertical neighbors, skewing the math. Now look at a hexagonal grid, measuring from the center to its 6 neighbors. All 6 center-to-center distances are the exact same length, eliminating the diagonal distortion problem. This uniform geometry led Uber to develop the H3 spatial index, which is now the industry standard for creating these multi-resolution hexagonal cells globally. By utilizing a hexagonal spatial index, complex geospatial floating point math is replaced by highly efficient string lookups in the database. The backend now has a highly efficient way to store the data, but it still has to interpret physical reality. Raw GPS signals are inherently erratic, prone to physical interference from tall buildings and atmospheric conditions. Engineers correct this noise using an algorithmic process called map matching. As you can see on the right, map matching takes those erratic raw coordinates and snaps them logically to the digital road network. The mathematical framework used to solve this is known as the hidden Markov model. In this algorithm, the hidden state is the vehicle's true physical location on a road segment, a state we cannot perfectly observe. The observed state is the noisy GPS ping received by the server, landing off the road vector. The algorithm calculates the highest probability trajectory to snap the ping into the correct location. The hidden Markov model transforms erratic mathematical noise into logical, physical reality. It provides the clean, accurate data the end user actually expects to see. The final handoff happens when the backend pushes this newly normalized, map-matched coordinate down the open server-sent event or WebSocket connection to the consumer's phone. The front-end client, leveraging tools like the Google Maps JavaScript API, updates the visual marker's position directly in the document object model. This changes the specific element without requiring a heavy reload of the underlying map tile itself. Because the client is only receiving discrete pings every 2 to 5 seconds, it uses interstitial animation. The front end smoothly animates the icon's movement from its old location to the new coordinates, preventing the marker from appearing to teleport or jump across the screen. When you pull back to a massive city-wide scale, you observe the entire system operating flawlessly in totality. It requires a deeply interconnected stack, adaptive ingestion at the edge, persistent web protocols across the network, precise spatial indexing in the database, and predictive algorithms on the backend. That seamless user experience is a carefully constructed algorithmic illusion. Failing to optimize even one layer of this streaming architecture will cause the entire city-scale coordination to collapse.